All right, thank you. All right, so this is a 23-year-old article, but it's nice because it illustrates a number of things. Early on in a course like this, it illustrates how flexible a regression approach is. In this case, there were 3 dependent variables. One was just years of completed schooling, a fairly continuous variable. In the middle 4 columns, the dependent variable is a 1-0 dichotomous variable, just takes on yes, completed high school, no, didn't complete. And it turns out that there's a regression technique that you can use when your dependent variable isn't continuous, but rather just takes on discrete values like 1 and 0. And then the final 4 columns is another kind of regression application that it's not used very much in developmental research and education research, and I've always been surprised at that. Suppose that you are predicting English language proficiency for dual language learners, okay? And you want to know whether the timing of gaining English language proficiency varies with a bunch of independent variables, right? You go out, get a sample of 1,000 kids, follow them over time, maybe starting at kindergarten, and measure every year what their English language proficiency is. And let's say that you run your study through 3rd grade. And you're able to observe for many of the kids that there's a point at which they gain proficiency. Let's say it's halfway through 2nd grade, most of the way through 1st grade. So you've got a timing of when proficiency was attained. But some kids make it into 3rd grade not having yet attained proficiency by some test that you're giving to them, right? So you know that they hadn't attained it by 3rd grade, but you don't know when after 3rd grade they might have attained it. Could have been 2 months later, it could have been 2 years later, right? So is there some way you really want to know that the time until proficiency is gained, that's the dependent variable, and you somehow want to account for the fact that for some observations, it's more than 2 years. If you're starting, 3 years, let's say you're starting in kindergarten and stopping at the beginning of 3rd grade. It's more than 3 years. It hasn't happened yet, but you don't know when it's happened. So do you take the number 3 and say, well, let's give everybody a 4? It takes 4 years. Or is there some way of taking advantage of this partial information that you have? You've got complete information for the kids who've attained proficiency by some point, and you've got partial information for the ones who still hadn't attained proficiency at the time your data collection finished, right? So this event history regression analysis is all about coping with those kind of dependent variables. And again, it's another wrinkle on a regression approach. In all cases, same list of independent variables. It's just a little bit of a wrinkle that we'll spend a significant amount of time on the 1-0 dichotomous outcomes. We may or may not get to the event history models. But let's start out with the first 4 columns, right? Years of completed schooling. A nice, it's not a completely continuous variable. It's lumpy. There's a hump at 12 years and maybe 16 years and maybe 14 years for people who completed a community college degree. But it's continuous enough for our purposes. So it turns out these kind of regression models that you're going to fit, people say that there are all these diagnostics. Is your variable truly normally distributed? Is it skewed? As a practical matter, the regression coefficients that you estimate, which is really the bottom line, doesn't depend very much at all about that. So this regression technique that you're learning is pretty robust to minor departures from normality, which is assumed in these models. So we're just going to apply a regular regression, and that's what we do in column 1. We've got a sample of, if you go down to the bottom, how many kids is it? Paul, at the bottom of the table. Uh, 1,323. Okay, so back up to the top. So we run a regression. We've got 15 years of family income averaged across those 15 years, age 0 to 15. Control variables that are in this regression are child race, child gender, maternal schooling, age of mother when the child was born, region, single parent family structure, maternal employment. A lot of control variables that are attempting to help this regression come up with a better estimate of what income effects are. And you end up with this estimate of 0.14 with a standard error of 0.02. All right, and that ratio is well in excess of what it takes to be statistically significant at the 1% level, the 0.001 level. So it's a highly significant variable in a statistical sense. And the interpretation I asked you to come up with, most of you got it. It's that a 1 unit change, which is a $10,000 per year, and this is averaged over 15 years, right? $10,000 per year for 15 years is associated with a 0.14 additional year of completed schooling. Is that a big effect? How do we think about that coefficient? Anybody, just unmute yourself.
It comes to just about 51 days, so it's like they stay in school for an extra 2 months, just under 2 months.
Right, and how much did it cost to get us that 2 months of additional schooling?
$10,000. Or for 15 years, that's
I'm sorry?
That's $150,000.
Exactly. So if somehow, suppose we had a income distribution program that provided all low-income families with $150,000 spread out over 15 years. You'd hope things would improve, but the association here is that the improvement is 1/7 of a year of additional schooling. That's a pretty minuscule change. Any other, somebody want to say that's big? All right. So,
sorry,
go
I have
ahead.
a question about the Um, that X variable. So is it across all 15 years, but is it looking at increments? Like I guess I'm not familiar with that. Usually,
No,
is it not an average? Is it not an average across all 15 years?
exactly. This study follows families every year for, in this case, in the case of these kids, for at least 22 years, I think. And the first 15 of those years, the family is reporting its family income. So you're getting this nice continuous measure of family income. And this analysis just takes those 15 reports of family income in the first 15 years and gets a per year average.
Per year average. Okay, so wouldn't then the interpretation be that an increase in 15,000 on average across all 15 years would result in a 0.14 rather than each year?
So the X variable is scaled in tens of thousands of dollars, right? It could have been scaled in dollars and you would have gotten 1/10,000 of 0.14. But it seemed, as we did this article, that it was better to rescale the income variable so that it produced coefficients that were more intuitive. So a 1 unit change, because we're talking about income scaled in tens of thousands of dollars, a 1 unit change in income is just an additional $10,000.
Mm-hmm. So it wouldn't be 100,
and it's an additional 10.
Sorry.
Yeah, so it's additional 10,000 per year, and the period over which we're getting this average is 15 years. Right, so 10,000 per year for the whole 15 years is $150,000.
But it's not. But if it's across all 15 years, wouldn't that kind of be taken into account the average income? But it's an increase in each year.
Well, it's an increase in the 15-year average, right? The actual X variable that gets stuck into the regression is a 15-year average income, right? So, you know, if your income is varying from 20,000 to 40,000, your 15-year average might be around $30,000 per year. Okay, so that's the kind of scale, and then because we ended up using a $10,000 scaling to get a 1 unit change in that X variable, a 1 unit change in X is amounts to a $10,000 per year for 15 years.
Okay,
which is going to be 150,000.
Okay, thank you.
Which is, you know, was extremely disappointing to get to see that coefficient. But let's ask a tougher question. Is that a causal estimate? So if we really did provide a family with $150,000 more income spread over 15 years, would we expect on average that the child's education would increase by 1/7 of a year? This is a different kind of question. We really want to end up being able to say causal things in this class. So the question is, can we think about this as an approximation to what an actual causal estimate would be? If we ran an experiment and actually took 1,000 families and gave them $150,000 spread over 15 years and compared them to an otherwise comparable group, a control group that didn't get that supplement, would we expect there to be a 0.14 year difference, roughly?
I think that
is this, go ahead.
I think there's definitely a correlation here, but correlation does not imply causation. And I think that there's a lot of like external variables that we would need to look at in addition in order to determine whether or not there is any sort of causation. just from this data alone.
Okay, so, right. So what kinds of things would lead you to think that that's not a causal estimate?
Well,
It is a correlation.
well, this was
Clean it
an
up.
experiment, correct? So we never actually gave I might have read the article wrong, but from my understanding of the article, we did not actually.
No, it's a pure correlation. Right, it's a non-experimental data.
We did not actually go through with an experiment. We're just basing this off of what analysis we can find from the numbers. And I think that I would need to go back in the article and look at the other like variables that were measured, such as like family education, for example, how well the students maybe did in school. I think there's a lot of like cultural and social factors that go into whether or not a student decides to retain in school or not. And I think that individual income, because like you can give, because there have been experiments where people have given people money, but if a person doesn't know how to manage that money, then that money is not going to do much good for them. So just from anecdotal evidence of what I've seen of people receiving money, I would lead me to see I would need much more information to determine whether or not this is a causation instead of strictly a correlation.
Can I also add on to what John said?
Sure.
I would strongly argue that you can't say this is a causal estimate at all. So something that John mentioned is that you can measure for other variables, maybe like education, maybe like generational income or something. But even if you had measured that, that still wouldn't mean you had a strong causal, you can't make a strong causal inference because one, this is the plus one more confound problem. Even if you had measured all these variables, someone can still come along and say, well, there's all these other variables that you haven't measured that could potentially explain the reason why X affects Y. So you have a bunch of different confounding variables that you cannot possibly control for unless it was a randomized experiment or something very, very close to a randomized experiment. But again, because you can't possibly have measured for everything, you can't say that there's a strong causal inference for this study and for the relationship between income and years of completed schooling.
What if you could measure for everything? Would you then
What if we could
be
measure?
convinced that this causal estimate?
If we can measure for every possible confounds?
Yeah, everybody draws up their list of possible compounds, and I'll go out and add it to this data set. I'll measure it and throw it into the regression. Is that going to lead to a convincing causal estimate in your mind?
In a hypothetical world, if we could measure like every possible little thing, yeah, I'd be a little bit more convinced. That's a really impossible hypothetical, isn't it? That's why we have randomized experiments.
Well, but we've got a small bunch of randomized experiments, and we've got 18 tons of correlational studies, right? So the challenge is to take non-experimental data and try to come up with something that's as convincing as a causal estimate as possible. And maybe the answer is there's nothing you can do. You just never, ever, ever take non-experimental data and think that you're even close to getting a causal estimate. But go ahead.
I'm sorry, no, you were in the middle of a sentence.
Well, but I was just going to say one of the points of this course is to talk about any number of approaches called quasi-experimental approaches, right? They're not random assignment, but they're quasi-experimental in that they take advantage of random assignment type variation in an independent variable of interest, and try to come up with causal estimates. All right, so let me give a couple of examples. In the case of income, there was a famous.
Sorry. So couldn't one also argue that you can't assume a causal inference because perhaps money can be a proxy for some other factor? For example, money is really related to the opportunities a person has had in life. So really, you're not supposed to be measuring money, but you're actually measuring some other underlying variable, and you don't actually know if what you're measuring is what you are measuring. Couldn't you also make that argument?
Right, but suppose I want to know, whether the next tax bill that Congress passes should provide more income to low-income families if what I'm concerned about is the educational attainment of kids growing up in low-income families. I want to know, to what extent will providing more income in and of itself change educational trajectories? That's a causal question, right? And everyone's poo-pooing the 0.14 as a guide to what the causal impact might be, and I do too. But if we don't run an experiment, can we come up with something that's close enough to a random assignment experiment to be convincing that we have a causal estimate? So just a couple of examples. One is took place in North Carolina, in the western part of North Carolina, where there just happened to be a wonderful developmental study called the Great Smoky Mountain Study, which sampled a large group of adolescents. They were age 12, I think, at the beginning of the study. They were followed for 15 years or more after that. And right in the middle of the study, there was a casino that came in. There were many Cherokee people living in this in the area that was being studied, and a lot of them fell into the sample. A casino came in and provided an average of $5,000 per year of a payment to people who could establish Cherokee heritage. And if both parents could, then the family got $10,000 per year. If only one parent could, then the family got $5,000. And if neither parent could, then the family didn't get anything. All right. So out of the blue, with no one expecting this, all of a sudden you had this what people would think of as close to an experiment, where money was given out differentially based on heritage. And so the analysis was able to look, control for a whole bunch of stuff around age 10, look at age 20, whatever, to see how much schooling that they'd completed, and to try to see, controlling for where the kids started out, whether the kids who didn't get anything had the lowest level, everything else controlled for, had the lowest level of schooling. The one parent kids had a higher level of schooling, and the two parent kids had an even higher level of schooling. All right. So in that case, you try to take advantage of what's called a natural experiment, where this money kind of appears out of nowhere and selectively to different families in the sample. And you could argue that the estimate that you get of income effects from that kind of study are much more convincing than certainly this correlational study, and maybe even close to being as convincing as if you actually ran an experiment. Reactions to that? You're all convinced?
I mean, when I'm thinking about this, I don't know. I've been thinking a lot about this, and this probably gets a little bit philosophical, but like, there's just no absolute way to know anything for sure. And the best we can do is just come up with the best possible explanation to support a theory. And that helps rationalize it in my head. Because there's not
Right. It's never,
a way to know anything for certain.
I couldn't agree more. It could be that what's true in Western North Carolina isn't true anywhere else. There's a problem with generalizability as well. But policy people want an answer. They really want to know, is anything going to happen in terms of child well-being, improving child well-being from some policy that costs taxpayers a lot of money that transfers resources to low-income families. And policy analysts need to have an answer to that. It might be, all the data are weak and correlational, so the tentative answer seems to be X, but nobody has any confidence in that. Or, it might be, well, there are these 2 or 3 interesting kind of quasi-experiments that, especially if they tend to agree on what the income effects are, end up being something that you can, if not count on 100%, at least think that they're probably telling you that there is indeed an income effect or there isn't indeed an income effect. So we're not trying to get to the perfection level, right, that you mentioned, Yarnisa, but we're trying to get close enough to be useful for theory testing or for policy making. All right, we will say more about this repeatedly over the course of the quarter. All right, so another problem with this kind of formulation is that we're fitting a linear regression, right? It's completed education is a function of income scaled in tens of thousands of dollars plus a bunch of controls. Parent education, family structure, employment, all sorts of stuff, right? If we throw a linear regression at the data, however the data are structured, we're telling it to come up with a line that fits the data best, right? And that's pretty constraining. Suppose the data, this is income, and this is education. Suppose low education or low income, low education, as income increases, education increases, but then for some reason, at high levels of income, education falls back down. All right, that doesn't happen, but suppose that were the case. So, Paul, can everyone see the dots that I just put on the board?
I think so.
Okay. Okay, so if that's the way the data are, and you try to fit a line, what's the line going to be? What's the best fitting line to these data?
I
No,
think
about
that a
line,
linear.
look at these.
Oh, sorry.
No, go ahead.
Oh, well, I think that a linear line would be quite dulled down, but you could do a quadratic line, like a curved line.
That's what we're getting to.
Oh, okay,
But
sorry.
let's start with let's start with just a straight up line.
Well, a linear line would turn flat because.
Exactly.
Yeah.
you're balancing, probably a little bit lower than that, but you're balancing negative and positive residuals and fitting something in the middle. There's no reason for it to be going up because of these points over here, or going up over here because of these points over here. So you just have a lousy fit. And if you just run this regression, you're going to get a coefficient that's insignificant, close to 0. And you're going to maybe conclude that there's no relationship between income and education, when in fact there's no linear relationship, right? So as was suggested, if we had a quadratic and added income squared, then we fit the data pretty well. I had a quadratic, it's a parabola, it's symmetric. And in this case, you're going to get a very good fit. And you conclude that the data are parabolic. You know, if the data were like this and then they kind of leveled out, and try to fit a quadratic, you wouldn't do very well, right? A quadratic, you're forcing it to be symmetric. So who knows what it would look like, but it would probably come up here and maybe go down here. It's got to be symmetric, so it's just not going to fit very well. So, you know, we had that problem with this article, and we came up with different approaches. You know, in fact, the data kind of looked like this. There was a pretty steep relationship between income and education below about $20,000. And then once you got above $20,000, let's say 100,000, there's still some increase, but the increase isn't nearly as rapid as in the low income segment, right?
Greg,
So the question is, yeah, go ahead.
sorry, I feel like I'm always interrupting you. I was wondering if I can ask a clarifying question.
Sure.
So in the Allison reading, he said that we should typically start with assuming a linear relationship, because you should always start, because you have no other reason to believe that it shouldn't be a linear relationship. But if we see a graph like that where it's clearly not going to be linear, should we still be trying to model a linear relationship using the data, or can we just kind of like skip that part and then try using all the other methods?
The latter.
The latter.
Right? And you know, there are various ways of trying to see what the relationship really is. And you know, one nice graphical way is to have income, education, and bin your data. By binning, we mean create some bins that contain the data, right? And within each bin, see what the mean education level is. With this bin, it's going to be like this. With this bin, it's going to be like this, like this, like this, like this maybe. So it's a very flexible way of taking a look at your data. And you're not imposing any, you know, we're not looking at these black points, it's just looking at the red points. And the more data that you have, the better the picture that you get from this. But what these points tell you is how far off you'd be if you did try a linear regression or a parabolic regression. And you know, it's pretty clear that a linear regression is going to substantially understate the slope early on and overstate the slope toward high income levels, right? A parabola isn't going to work. So maybe you should think about some other kind of function. And one of the things that we did in the paper is fit an equation, education A plus B1, the natural logarithm of income, plus a bunch of controls. So if you take the natural log of income, you're fitting a relationship that is increasing, but it's increasing at a decreasing rate. So, you know, that's not bad in terms of what this data look like, what these data look like. So that's one way of accounting for nonlinearity. Another way, which we also use, which is more flexible, right? The linear relationship constrains you in an important way. You've got to have this increase at a decreasing rate. But suppose we were flexible in saying, all right, up to $20,000, let's allow for one slope, but then everything above 20,000, let's allow for a different slope. This is a spline function, sometimes called a piecewise linear function. And this is nice because you're opposing some structure. You're saying there are two linear segments, not just one. And you're allowing it to fit. You have to specify what the cut point is, in this case, 20,000. Turns out we searched around the data and figured out what the best point was. You're fitting a line, a slope up to 20,000, and then allowing for a totally different slope above 20,000. Okay, so how can you do that in a simple regression context? Well, it turns out there are various ways of tricking regression to bend it to your will. And in this case, if you fit the equation, education is a function of income. But now say it's also a function of a 1-0 indicator, whether income is above 20,000 plus this 1-0 income above 20,000 times income. It turns out you get exactly this kind of functional form. So everybody sees, this is just, you look in the data and every time an observation has an income above 20,000, this variable gets a value of 1. Whenever it's less than 20,000, it gets a value of 0. Okay, that's it's called a dummy variable. You create a 1-0 variable, and then you just multiply that 1-0 variable times income in your action. So why does that work? So ask me questions, but maybe in a couple of minutes after I just show you how this works. So let's first take, for children in less than $20,000 families, what equation is being, what is this reduced to for those families? Education, A plus B1 income plus, what's C1 times whether it comes above 20,000?
Would it be Sarah?
Would it be what?
Sarah?
0?
Yes.
That's what you said? Yes, exactly. And then what about the interaction of whether
Same.
above 20? Same thing.
Mhm.
So we're just plugging in to this equation. What would the less than 20,000 kids look like? And for them, this value is 0, and the first part of this interaction is 0. So their equation is just education as a function. This B1 coefficient is going to capture what their income effect is. For the greater than 20,000, you're going to get education A plus B1 income. Now, these dummy variables switch on. So we're going to get C1 times what? 1. Right? Everyone with an income above 20,000 is going to have a 1. So you're just going to get C1 plus C2 times, all these are 1s. So you're going to get C2 times income. So in other words, for these greater than 20,000 people, you're going to have education, you're going to have a new constant, A plus C1. Before the constant was just A for this group, now it's A plus C1, plus, and now the coefficient on income is B1 plus C2 times income. All right, and it all comes from just estimating this equation. So put that table 3 back up, Paul.
Okay, and there's a hand.
Oh, sorry.
How do we drive C1 and C2 again?
C1 and C2 are just 1, 0 variables.
Okay.
Well, no, C1 and C2 are the coefficients that you estimate. And they're coefficients on this 1, 0 variable that kicks to a value of 1 if income is above 20,000, 0 otherwise.
Right.
Right?
Got it.
So, okay. So it's 0 times C1, 0 times C2. So it drops out. Okay, and if you share, so take a look at the spline function that gets estimated. So this coefficient B1 is 1.30. Used to be 0.14, now it's 1.30. And the way this is estimated, the second number is the difference between the under 20,000s and the over 20,000s. So the C2 is minus 1.23. Okay, so what does that mean? The slope here is 1.30 per $10,000 per year. And what's the slope here?
Should I go back to sharing?
Well, I put it up here. This coefficient is minus 1.23. So what's B1 plus a minus 1.23?
Isn't that coefficient 1.70 on table 3?
I'm sorry. So we're just looking at the spline functions, right? The first coefficient is 1.30. That's the under 20,000 slope. And then the difference between the under and over 20,000 is minus 1.23. So this is 1.23, but this is the difference, 1.30 minus 1.23.
So why wouldn't that value be negative 1.17? Because I thought the coefficient for negative 1.17 represents the difference between your incomes greater than 20,000. So on the right side of whatever your vertical line is, and then minus whatever is left of that, which is less than 20K.
So we're estimating the difference. So it's 1.23 smaller than what the estimate for B1 is, right? So 1.30 minus 1.23 is plus 0.07.
Sorry, where
Okay.
did minus 1.23 come from?
It's this coefficient.
And it's in the table?
Oh, I'm sorry. All right. How about 1.17? Now I got 1.23 stuck. So I often make mistakes and I never mind being corrected for the mistakes that I make. All right, so what's the difference? Now it's 0.13, right? Sorry. So you've got this estimate that's fitting the data in a more flexible way than just a straight line, where increments to income, $10,000 increments to income for low-income families are associated with, almost 10 times as much completed education as what we estimated before. 0.14 has become 1.30, and above 20,000, the slope is still positive, but it's just creeping up very slowly, right? Almost as slowly. If you think about the data, it's a pretty small fraction of families, less than 20,000. The heart of the data is above 20,000. So we had 0.14 before. If we take out these low-income families, that shrinks a little bit to 0.13. But what's really remarkable is how much bigger the coefficient on low income has gotten. So it's still not causal, but it's not, pathetically small as it was with a seventh of a year increment to education that we got when we just fit a single line. Okay, so is this stunned silence, or is this highly aware, let's move on silence?
So it makes, conceptually it makes sense. And I think I'm just processing and just putting it all together in the way that you kind of explain it. And some of the terms kind of have a new meaning to me as far as the way they kind of, I may have learned them, but just try, what does it mean to have a predictive why? Just those type of things I'm just rethinking over again in this as we're looking through this formula, so.
Okay, well, there are a lot of these little tricks that you can do to regression to come up with a better idea of what the relationship is. And the log linear form was one, but the spline imposes no necessary relationship between the two segments. So in that sense, it's pretty flexible. You still are assuming a linear relationship below, a linear relationship above. That may not be true, but it turns out if you actually look at the data scatter, this ends up doing pretty well. All right, so go ahead.
So I'm wondering how to interpret it. So I know we talked about interpreting. So for example, if I'm looking at the table where it says the spline function, I'm looking at income less than 20,000, then the coefficient is 1.3 and it's significant. When you're talking about it in terms, like practically speaking, we can say that's 1.3 years in schooling, but can you also interpret that in the difference between like undergraduate degree and like a graduate degree, for example, like a one-year master's program? So in that case, that would be seemingly a lot more significant if you had obtained a graduate degree versus just an undergraduate degree by having that 1.3 years of difference, because there are graduate degrees that do have 1 year, right? So I'm just wondering, like, how would you interpret that instead of just saying a 1 unit change, which is $10,000 in family income over 15 years, translates to 1.30 years of completed schooling? Because how would you know if you're talking about schooling in high school or middle school versus high school, or like undergraduate versus a graduate degree? Are we simply just
Well,
because
look at the
ages?
Yeah, you have to look at the distribution of the sample, and in this case, the sample, there's much more action. This is also a somewhat dated sample. There's much more action in completing high school, in going on and getting any post-secondary education than there is up at the, graduate from college and maybe go on to get a master's degree. So, I would think the economist in me would turn to the big literature looking at the economic payoff in terms of wages to additional schooling. And the consensus from that literature is that every additional year of schooling, it can be another year of high school, another year of college, is associated with about a 10% gain in lifetime earnings. 10% more over your earning career. So this is more than a year. It's 1.3 years. So we might be talking about something like a 13% increase in lifetime earnings. And lifetime earnings, it's average earnings for this sample is probably around $50,000 times a career of 30 years, right? That's starting to be a significant amount of money. And if you're 13% more than that, that's also a significant amount of money. So there are various ways, and it's very important to draw on those various ways to try to convey to readers what the importance of a coefficient or unimportance of a coefficient might be. And that's one of the things that we'll talk about a lot in this quarter as well.
I also had
All right, so
sorry, can I ask?
Sure.
So I had a question about the difference. So 1.17, it's significant. So does that mean that the slope for more than 20K is significantly different from less than 20K? But we don't know if
exactly.
But we don't know if the slope of 0.13 is significant, though, right? We were not told that.
Yeah, there are different ways of estimating a spline function. One of them is this way, where it is true that minus 1.17 being significant tells you that there is a highly significant difference between this slope and this slope. there's another way that you can formulate this equation so that you end up getting the 1.30 and a significance test for that, and then the 0.13 and a significance test for that too.
Okay.
Right? But if you just think about it, we've got 80+% of the observations above 20,000, and when we just fit an overall line, the slope was 0.14, the standard error was 0.02, and that was a highly significant coefficient, the 0.14. So now with almost as much data, we're getting a 0.13, and the standard error might go up from 0.02 to 0.03, but it's still going to be highly significant, I would bet. But they're just, you can run it in a way that gets you exactly what you want.
Got it. Thank you.
Actually, that's a good motto for the class. There's always a way to run it to give you exactly what you want. Okay, so Paul,
There's another question. Well, there's another hand.
Okay, sorry.
Excuse me.
All right.
So I had a question about the formula that you just wrote on the board about the spline.
Yes.
So if we just move the first point on the 20K to the point on 0, 0, and then do a linear regression, and then just move those and calculate the slope, and then move those points back up again, will this have the same result as we have calculated here?
You want to move this back, this point back to 0?
Yeah, put it on the 0, 0 point there. Yeah, here. Yeah.
Okay. So then 100% of the sample would be above 0, right? So you'd end up with where you started from with that linear relationship. You'd have some constant, who cares about the constant, and a coefficient of 0.14. I'm not sure how it would divide up. I mean, you're not really fitting 2 segments anymore because there's no data to the left of the 0, 0 point.
Okay, yeah, we just fit lines separately to those different below 20K and above 20K. We just do that separately. 2 different lines.
You mean without forcing them to be connected?
Yeah.
Okay, so I'll tell you what. Let's continue talking for 5 minutes. We're pretty much at time for everybody else. Paul, we didn't get to the description of the data set.
Yeah.
But we can do that in the lab maybe very briefly.
Okay.
So, this is supposed to be a preview to coming attractions of the course, right? So if you're not getting it the first time around, you'll have ample opportunities to get it in the second or third time around. I know that people are coming from into this class from very different kind of backgrounds in terms of the preparation and how much statistics they've had and so forth. So we're going to be holding hands, and the lab is going to kind of march you through step at a time. And our office hours are always open for people who need, who have questions. So thank you for turning on your cameras and turning on your mics. I wish we didn't have the kind of delay between when I was speaking and when you were speaking. That's kind of awkward sometimes. But I thought it worked okay. We're going to have microphones working and cameras working and everything by next week. So I might join in with the lab for a little bit, but I'll certainly see you next Monday. So bye, everybody. And whoever asked that question, why don't you hang on and we can talk for a few minutes.
Greg, can I ask you one quick question about the syllabus? I just realized I forgot to ask earlier.
Sure.
For the homework on the syllabus, I think you stated that the homework would be released on Monday, but in an email you sent out, you said the homework would be released after lab. So I just wanted to clarify when the homework would actually be released.
Oh,
So the problem set homework,
Mhm.
just to be specific, because I realize there are other homework.
Yeah, the non-short answer ones.
Yeah. So the problem set homework is going to be released after class. I've released it for this coming problem set already before class. Depending on what happens in class, I might upload it later because we might want to change something depending on what we covered or didn't. It will be posted at the latest by after lab, so sometime on Tuesday, but likely by end of the day on Monday. And if I can do it earlier, sooner.
Great, thank you for the clarification.
Also, if we want to hang on for the conversation afterwards, can we stay around or?
sure, yeah, everybody can hang on, that's fine. So who was asking a question? Is it Amin?
Yeah, it was me. Yeah.
Okay, and I didn't quite follow, so could you repeat that, please?
Okay. So we separate our data to two different parts, like below 20K income and above 20K income, right? So if we
That's effectively what we did.
Yeah. So if we do a linear regression one time for the below part, the first part, and just do another one for the second part. So what I'm trying to say is that like move the point on the first, like on the 20K income to the 0 point. So what we essentially do is that we move all those points just in the center of the plot. So we do another linear regression on those. So we calculate, so we have the slope then, and we can have those points like moving again up there.
So let me.
I don't know if I could like explain what I meant.
Yeah. So what we're really doing here is fitting this line and fitting this line. Oops.
Yeah.
Right.
Exactly.
So we'll get a.
Yeah, what I was asking is that do these like get to the same results here? So are we doing the same thing now or not?
This is essentially what we did.
Oh,
right. We fit two lines, right? One of them is the B1 income. That's this line, right? And the other is the B1 plus C2 income, and that's this line, right? So if we looked at the constants for in the output, you know, the B1 line, the less than 20,000 would have this intercept, and then the greater than 20,000, the difference in the intercepts would be, well, you can see that A plus C1, right? So C1 is going to be the difference in the intercepts that you get, just in the same way that C2 is the difference in the slope. So you're going to have this 0.13 all the way back to 0 and beyond. You can have the 1.30. So it's like fitting two lines. You're just not paying any attention to this portion of this line or this portion of this line. So I think we're saying the same thing.
yeah. Thank you. I just wanted to get a better intuition of what the formula is doing. Thank you.
Sure. So any other follow-on questions? Anybody?
Building on that, I was wondering if you see this trend in your data, could you just run, or could you just, yeah, could you run a regression without that kind of complex formula, like the plus C1 plus C2 times income? Is that a reflection of like prior to doing two different regression formulas? Or do you have to include that in like the syntax when doing a piecewise linear regression? Does that make sense?
Yeah, you just have to create this 1, 0 variable, depending on whether the income was greater than 20,000, and then
Oh,
create an
okay.
additional variable that's that 1, 0 times income. It's just
Okay,
those two
okay, that makes
variables,
sense.
and you throw those two variables in, and you're all set.
Okay.